So let's begin. Last lecture of this course. I will be a little quick this time because there's some things which I wanted to include. So, but anyway, it will be reasonable. There are so now scaling relations. So in astrophysics, whatever branch of astrophysics you go to, you will encounter scaling relations. Okay? We have scaling relations basically relate one parameter to another parameter. And often in astrophysics, not always, the scaling relation will be a power law. And we have encountered during this course several power laws. So in the case of galaxies, the global parameters of galaxies obey certain scaling relations. And these scaling relations are between the fundamental physical properties of galaxies, like their luminosity, their size, their surface brightness, their rotation velocity, etc. They're important for several reasons. First of all, they tell us something about the internal properties of galaxies as a whole. And they must also arise naturally in theories of galaxy formation. So if you have any theory of galaxy formation, that should predict the observed scaling relations. And not just one of them, but all of them simultaneously. In the case of disk galaxies, the most important scaling relation is between the rotation velocity and the luminosity. And this is known as the Tully-Fisher relation. So in the 1970s, Vera Rubin and collaborators started measuring the rotation speeds of galaxies for the first time. Okay. And what they found was what you would expect, the rotation velocity, the expectation was that the rotation velocity will rise and slowly fall off as a 1/√r kind of function. But what was actually happening was that the velocity was rising and it was staying more or less constant. This was a very large discrepancy. And this led to the discovery, or at least the hypothesis, that this flat rotation curve is being caused by the presence of dark matter in these galaxies. So there is, just like the baryonic matter is sort of centrally peaked, the dark matter is also centrally peaked. It has a certain different profile, not an exponential base or surging bulge, but it has a certain flat, certain profile, which leads to the flat rotation curves. And this quantity is called Vmax, the maximum velocity. And what Tully-Fisher found was that if you plot the maximum velocity of a particular galaxy with a regular rotation curve with its luminosity, then those were strongly correlated by a power law with the index of 3 to 4. And scatter in the Tully-Fisher relation is smaller at longer wavelengths. And Tully-Fisher is an important distance indicator. How to measure distance with Tully-Fisher? We've done this sort of thing before.
Measure the rotation velocity, use the Tully-Fisher to get the velocity.
Correct. Measure the flux, and once you know flux and luminosity, you know distance. Okay. So absolutely straightforward way of doing things, but of course you have to calibrate the Tully-Fisher relationship at some distance. So you have to have some independent measure of distance for some galaxies at least, so you can calibrate the relation. And once it is calibrated, you do exactly what Varun was suggesting, which is you have a calibrated relation and you measure distance. So this is the Tully-Fisher relation in various bands. So B band is the shortest wavelength band, and then V, and then R, and so on. So you can see that the scatter in the B band is quite high. By the time you come to the H band, the scatter in the Tully-Fisher relationship is quite small. And the reason for that is that here you are sampling light from the massive stars, which may be not uniformly spread throughout the galaxy. They'll be mostly in the spiral arms. But here you are sampling the light mostly from the low mass stars like the G and M type dwarfs.
And then you get a sort of tighter relationship. So why is this so interesting? It connects a property of the dark halo, the maximum circular speed, with the product of the net integrated star formation history, which is the luminosity of the disk. This implies halo-regulated galaxy formation and evolution. So far, whenever we've talked of galaxy evolution, we have sort of brushed aside the dark matter halo. But really, it is the halo which is regulating the growth of the galaxy and so on. Because it's the halo that dominates in mass. Dark matter halo contains most of the mass of the galaxy. Baryonic mass is much smaller. The scatter is remarkably low. There is some important feedback mechanism involved, which we do not understand yet. The Tully-Fisher relation offers some important insights into the physics of disk galaxy formation. Okay. So now people said, okay, this is a scaling relation for spirals. Is there an equivalent scaling relationship for ellipticals? So now in the case of ellipticals, you can't use the maximum rotation velocity because they don't have a maximum. They don't have a well-defined rotation curve. The rotation can go up and down, can be anything. So you can't use rotation velocity. But what you can use in its place is the velocity dispersion, what is called as the central velocity dispersion. So you take a spectrum of the central region of the galaxy, and there will be a velocity dispersion there. You measure any line, that line will be broadened. And why is it broadened? It's broadened due to the Doppler effect. So it's called Doppler broadening. So this Doppler broadened line, if it is broadened more, the standard, this sigma will be higher. If it is broadened less, then the sigma value will be lower. And it's usually measured in kilometers per second. And that, if you plot against absolute magnitude, this is absolute magnitude in the B band, but you can plot it absolute magnitude, any other filter, or plot luminosity instead of absolute magnitude, doesn't matter. Log luminosity, if you plot, then you will get again a power law relationship between velocity dispersion now, instead of rotation velocity, velocity dispersion, and the log luminosity. So, okay. So now for elliptical galaxies, there is another relationship which holds, which is called as the Kormendy relation. Now, this is a measure of the size of the galaxy, the log of the size in kpc. Okay. And this is a measure of what is called as the central surface brightness, or in this case, the central surface brightness at the effective radius. So some measure of how bright the galaxy is. How much is it? How bright is it? Not in terms of its total magnitude, but in terms of its surface brightness near the center. Okay. And obviously, this is a magnitude scale. So brighter galaxies are there, fainter galaxies are here, larger galaxies are here, smaller galaxies are here. You get this kind of, again, sort of power law relationship between size and surface brightness of the galaxy. And it turns out that this relation tells you something about galaxy formation, because this relation is not fundamental. It can be combined with the Faber-Jackson relationship to give you a higher dimensional plane, which is known as the fundamental plane. And both the Faber-Jackson relation and the Kormendy relation are projections of that higher dimensional plane, which obviously relates this and this to the luminosity and the velocity dispersion. So what it basically tells you is that, given what the fundamental plane says, that if you know the velocity dispersion and the size of the galaxy, you can predict its central surface brightness, you can predict its luminosity. And as it turns out, you can predict many other things also. So elliptical galaxies are particularly simple systems to understand. And that is why we can use many of its correlations are really, it's a function of only two variables. So once you know, measure two parameters for two independent parameters of an elliptical galaxy, you can predict all its other properties. Okay. So now, from the virial theorem, the dynamical mass goes as R sigma square. Okay. Luminosity L is proportional to IR square, where I is the mean surface brightness. Now, if mass to light is constant, then M proportional to IR square is proportional to R sigma square, and IR is proportional to sigma square. Okay. So, if ellipticals formed via dissipation-less mergers, dry mergers, remember we talked about dry mergers, kinetic energy per unit mass, which is this quantity, sigma square, remains constant, implying if this is constant, then the size is proportional to the inverse of the mean surface brightness. Okay. You can work out the algebra here. It's very straightforward. If ellipticals formed via dissipative collapse of gas, then it goes differently. The surface brightness goes as mr raised to -2, and this implies r goes as I to the power -0.5. So now, this is like a wet merger. This is like a dry merger. Dry merger should give you this kind of Kormendy relation. A wet merger should give you this kind of Kormendy relation. But the actual Kormendy relation is this. So what does this indicate for elliptical galaxies? Huh? It's sort of almost halfway between the two, no? So what does that indicate? Both are true. Both are true to some extent. What that means is, at some point in its history, the elliptical galaxy underwent wet mergers, but it also underwent dry mergers at some point in its history. So it underwent both kind of mergers. And if our picture of elliptical galaxy formation is correct, in the early times, the elliptical galaxies, when they were forming most of their stars, they were undergoing large numbers of wet mergers early in their life. They built up most of their stars and they become quite big and massive, and they converted all the gas they had into stars. And after that, in the late stages of their life, they grew by just doing dry mergers with smaller galaxies or similar sized galaxies, and grew in size. So the Kormendy relation, a simple relation which is very easy to measure, tells you something about the formation history of elliptical galaxies. Okay, so just to confirm what we discussed yesterday, we will have the exam on Friday, 27 September. 50% weightage for this exam. It's going to be 2-hour, 15-minute exam. If needed, we'll extend it by 15 minutes. Short answer questions based on all lectures, with most questions from lecture 7 onwards, because we haven't asked you anything on that. Close notes, close book like the last time, and please bring a scientific calculator. Yeah. So now there are other scaling relations, now involving the supermassive black hole at the center. So this is the circular velocity, kilometers per second, that is this kind of velocity. And this is the bulge velocity dispersion, right? And these are correlated with each other. So if you have a spiral galaxy in which there's a disk which is rotating, but there's also a bulge at the center, the bulge and the bulge velocity dispersion and the disk velocity are correlated. Then dark matter halo mass, right, is correlated with the supermassive black hole mass. So more massive galaxies will host a more massive halo at its more massive black hole at its center. So these kind of correlations also exist. And you can see these are always power laws, right? And therefore, the scatter seems small, but it is, remember, it's on a log scale. So you could easily have 20-30% scatter in all these relations, but in these kind of visualizations, it appears small. Yeah.
Can it keep the dark matter around it?
Yeah, yes. Gravity. So yes, it can eat the dark matter. No problem. But remember, it eats so little matter, it doesn't affect the presence of a black hole, doesn't affect the overall. See, we have a pretty nice big black hole, but it is about 4 million solar masses, right? And the mass of our galaxy is somewhere between 100 billion and 200 billion solar masses, just the stars. So 4 million compared to 200 billion is nothing. So it won't affect the overall dark matter budget of anything. Yes, but it will swallow, because what does dark matter feel? It feels the gravity. So if the gravity is strong enough, it will pull in dark matter. Right. Black hole mass on the y-axis and the bulge stellar mass on the x-axis. So the bulge, now this is also very curious, because what is happening here, the size of the bulge is several kpc. The Schwarzschild radius of the black hole is like solar system sized or smaller. It's very tiny. And it is affecting somehow, the black hole knows what is the bulge mass, or the bulge knows what size of black hole to build. So this clearly indicates to you that there is has to be co-evolution of the black hole and the bulge. So the bulge and the black hole must grow due to physical processes that are similar. Perhaps the same physical process that is responsible for the growth of the bulge must also be responsible for the growth of the black hole. And that is why this is getting you a power law relationship between the mass of the black hole and the mass of the bulge. Now, this also observationally is very interesting. Measuring the mass of a black hole is very difficult, because you have to get a spectrum of the central regions accurately. For this, you can easily decompose the light from the bulge and the disk, take the light of the bulge, okay, do something called population synthesis modeling, which we haven't discussed. And once you do that, you'll be able to get this quite easily. Just from some multi-band images, you'll be able to calculate this. You don't need a spectrum. And then, given this relationship, you will be able to calculate the black hole mass. And remember, it's always the bulge stellar mass, not the disk. It's immaterial what the disk stellar mass is. So, are there any galaxies where, if this relationship holds, are there any galaxies you can think of which will not have a black hole? Sorry? Irregular galaxies, that's absolutely right. Also, there are a small number of galaxies which are what are called bulgeless galaxies. They're pure disk galaxies. This bulge goes smaller, 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 and in some galaxies it disappears altogether. Only a circular disk is there. In such galaxies, the black hole will be absent. So, and in irregular galaxies also, the black hole will be absent. But in every other galaxy, the moment you have a bulge, you will have a black hole. Bigger the bulge, bigger the black hole. So the biggest black hole will sit in the biggest elliptical galaxies.
The differential between stars on the bulge and the disk.
So this is something which I haven't covered, but the light profile of the bulge and the light profile of the disk are very different. So the disk has an exponentially falling off light profile, and the bulge has a light profile that falls off much steeper initially and then flattens out. That is called as a Cercic profile, or a special case of that is called the Divocular's profile. So what you do is, you given an image of a galaxy, you break up the light into the bulge and the disk by doing an analytic fit. So you have the analytic light profile for the bulge, you have an analytic light profile for the disk, which is the exponential. You do a simultaneous fit of both these profiles to the light distribution of galaxies, of that galaxy. And then you will be able to separate it. That, okay, if this galaxy has this profile for the bulge, this profile for the disk, you can then integrate under that profile and get that, okay, for this particular galaxy, 20% of the light is bulge, rest of the light is 80% of the light is disk, right? And you can do that for every galaxy. And my first paper in my PhD thesis was to write a code to do exactly this. So you can break it up, and then you know the light from the galaxy. Now you do this in many different filters. So you measure the total magnitude of the bulge in many different filters. And then there is a technique called stellar population synthesis, which fits the star formation histories and the IMFs and everything to reconstruct to obtain what is the star formation history of the galaxy, which is the star formation rate as a function of time. And if you integrate that function, then you will get the stellar mass. Because you know how many stars were formed at different points in time, then you will get the stellar mass, total stellar mass of the galaxy. And it is a pretty accurate estimate, because you lose, only thing you lose is some remnants, because the most massive galaxies would have gone supernova, massive stars would have gone supernova. You miss the remnants, so you can add back the mass of the remnants, and then you'll get the total mass of stars in the galaxy. So that's how you get this quantity. I mean, it's not absolutely straightforward, but it's not difficult. Yeah. So dark matter halos. Many of the galaxy scaling relations may be driven by the properties of their dark halos. It is possible to infer their properties from detailed dynamical profiles of galaxies and some modeling. And what people have done is they've done numerical dark matter simulations. And these suggest a universal form for the dark halo density profile. And this is known as the NFW profile, after the authors Navarro, Frank, and White, who first proposed this kind of function. So there is some kind of scale length which is there, and then there is the central density of dark matter. So what this tells you is how does the density of the dark matter halo change as a function of radius. Radius meaning distance from the center of the galaxy. So these are galactic halos. And of course, this number and these two free parameters will vary from halo to halo, but the shape will remain the same. So this is the dark matter halo profile. So that those are velocities that are plotted, but you could plot density also as a function of radius. So it peaks at the center, right? This kind of profile. Okay, so this coming back to the 1937 Zwicky work. So here are the numbers. So this is the virial expression, virial theorem. And for typical clusters, the velocity dispersion of the galaxies in the cluster ranges from 500 to 1500 kilometers per second. And the radius of the cluster could be 3 to 5 megaparsec. And this will give you a cluster mass of 10 raised to 14 to 10 raised to 15 solar masses. These are very massive clusters. Huh? These typical clusters are 100 to 1000 galaxies. And the luminosity of the cluster is 10 raised to 12 solar luminosities. And therefore, the M over L ratio comes out to several hundred. We said Zwicky calculated 300, so but it'll come in this range. And so, of course, he said something is very wrong. So besides the dark matter, Zwicky was also not aware of the existence of the dominant baryonic component of clusters. What do you think this is? IgM, ICM, it's called, intra-cluster medium. Okay, so it turns out that in clusters, most of the baryons are not sitting inside the galaxies. Most of the baryons are sitting outside the galaxy in the intra-cluster medium. Okay, this is the medium between galaxies of the cluster. So it's within the cluster, but outside the galaxies of the cluster. That intra-cluster medium contains very large amounts of hot gas. And how do we know that there is a lot of hot gas there? What will happen if you have a lot of hot gas? How will you detect it? Sorry? Emission in what? Which kind of telescope will you use? Infrared? No. X-ray. Hot gas. It's going to thermally emit. There will be thermal continuum emission from the hot X-ray emitting gas. So you just observe it with an X-ray telescope and you will see see it directly. So Zwicky was not aware. In fact, nobody was aware until the first X-ray telescopes were flown into space, or actually, I don't know whether it was discovered when we used to have rocket bone X-ray telescopes used to be there. Balloon bone X-ray telescopes used to be there in the early days. But I don't know when it was actually discovered. But now we know with modern telescopes like Chandra and XMM Newton and so on, we have observed many thousands of clusters now, and most of them show hot X-ray emitting gas. Okay, so now this dark matter, what is this business? So we have, most people nowadays assume that dark matter is some kind of particle. Okay, could it be massive neutrinos? Perhaps. Could these be weakly interacting massive particles? Okay, so there's this class of theories in particle physics called SUSY, or supersymmetry theories. They predict several particles. The least massive SUSY particle is called the neutralino. Okay, and there are also gravitinos, photinos, excinos, and so on. And these are all pretty massive particles, very high energies, but they're weakly interacting. Obviously, you need that. You don't want it to start emitting light and so on. So they could be these. Some versions of quantum chromodynamics, okay, predict the existence of axions, and they could range widely in masses, and they could interact electromagnetically. So if axions exist, there could be some possibility of detecting them electromagnetically, and many other speculative possibilities. So I think this must be the longest standing unsolved problem in astrophysics today, which is the dark matter problem. That we're more or less at the same spot we were 40 years ago. This has not happened with anything else, where we have made very little progress in 40 years. So that's one big unsolved area of astrophysics. What is the nature of dark matter? But what we do know that what kind of dark matter. So one thing is, there are two types of dark matter. One is called hot dark matter. So here the dark matter is relativistic. So must involve low mass particles such as neutrinos. And their streaming erases the small scale density fluctuations. So big structures form first, then later fragment. This is top-down structure formation. Right? And then the other is the cold dark matter, right? Here matter, whatever dark matter particles are there, they move relatively slowly. So all these axions, WIMPs, etc., will fall into that category. And in such cases, density fluctuations at all scales survive. And small fluctuations collapse first, then larger ones. Okay. This is the bottom-up structure formation and is the best match to what we observe. So what do you mean by what we observe? Remember those large-scale structure maps that we made with SDSS and 2DF and so on, and we saw those voids and other filaments and other structures. Those structures are very closely aligned to what the CDM predicts, and they're not very well aligned to the hot dark matter. So that's why people will talk of lambda CDM cosmology. Okay, lambda stands for the cosmological constant, but CDM here stands for the cold dark matter. So we believe we live in a cold dark matter. But it could be also that there is some kind, a little bit, it doesn't prevent hot dark matter from existing, but it is just that it is less in quantity than the CDM. The dominant component has to be CDM. There could be a little bit of hot dark matter present. Okay. So now cosmology. So you have a whole course on cosmology. So I'm only going to have a couple of slides on cosmology. So just to write down the cosmology independent expressions. So in cosmology, generally, basically, you need 3 numbers to define your cosmology, right? You need to know what is the expansion rate of the universe at the present time. You need to know what is the energy density of matter. And this matter includes dark matter. You don't need to separate them. You need to know, because as far as cosmology is concerned, matter is matter. I mean, all matter, anything that interacts gravitationally, that's matter. So that dark matter and baryonic matter. So that is called omega m. We should write down. So you need the value of H naught. The Hubble's constant at the present time. You need the value of omega matter, and you need a value for omega lambda. So if you have these 3 numbers, your cosmology is defined for you. Now, what we also have found in recent times, that within the error bars that we are able to measure, omega matter plus omega lambda is equal to 1. And this indicates, so this is referred to as a flat universe. So the total value of lambda is this. So what is omega lambda? Omega lambda is the energy density of something known as dark energy. And this dark energy is responsible for the acceleration of the universe. We won't go, you will go into great detail in all these things in the cosmology course. But let's look at the simple equations that you can write, cosmological equations you can write down without worrying about those parameters at all. Okay. So definition of redshift, this is the definition. Wavelength, observed wavelength is equal to 1 plus z times the emitted wave. So you know that, okay, I'm seeing the H alpha line. I know it's a wavelength. I calculate, measure lambda observed, and I plug in the wavelength of H alpha. I do this and I calculate psi. Scale factor. So scale factor is nothing but, the scale factor is assumed to be 1 at the present time. And the universe was obviously smaller in the past because it's been expanding. So by what factor were all lengths contracted is given by this A parameter, and that is equal to 1 over 1 plus z. So at redshift z, let's say redshift 1, 1 over 1 plus z is half. So what that means is you take any two widely separated objects, say you take the Virgo cluster and the Perseus cluster, and you go back in time. You measure their separation in megaparsec today. You go back in time to redshift 1, then that separation would have been half the separation that what it is today. And if you go to redshift 2, the separation would be 1/3 of what it is. That is what is meant. So this is a measure of the length scale of the universe. Now, volume obviously goes as 1 over a cube. So the volume, co-moving volume at redshift z is 1 over 1 plus z cube. So if you take any volume in the present universe and you say shrink it down to redshift 1, how much volume would it have occupied? 1/8. 1/8 of the volume that way. So this is very important because when you are calculating any kind of density, right, co-moving number density, you have to take this into account. So if you are counting the number of galaxies per unit volume per megaparsec cube, you will find the density to be much higher at higher redshift just because the universe was smaller. Same galaxies may have been there, but you'll say, oh, they're 8 times higher, but you have to correct for that. So we always talk of co-moving volume, densities per co-moving volume. Right. Then there is the temperature of the cosmic microwave background. It has a temperature of about 3 degrees Kelvin right now. Right. But at the last scattering surface, the temperature will be much higher. So the last scattering surface from which we are getting the cosmic microwave background radiation, that is at a redshift about 1100. So this will be 1101 if you want, T naught times 1100. So it will be 3300 Kelvin, approximately 3000 Kelvin. Time intervals. So because of the expansion of the universe, time also gets dilated. So if you observe a supernova going off at redshift 1 in a redshift 1 galaxy, the proper time of that supernova, suppose it brightens and fades in 60 days. What will you observe it on Earth over here? You'll observe it to brighten and fade in how many days? Huh? 1 plus z. So z is 1. So 120 days. So it will take 120 days to brighten and fade. So this happens. Then the cosmic microwave background, because the universe is expanding, the photons are also losing energy. Right? So at 1 plus z, the photons will they goes as 1 plus z. So at redshift 1, the photon would have double the energy that it has now. So if you just take the peak of the CMB spectrum, the wavelength of that, the wavelength would be shorter by a factor of 2 in galaxies at redshift 1, right, in the past. And because the volume is going down as 1 plus z cube, and the CMB photon energy is going as 1 plus z, the CMB energy density would go as 1 plus z to the 4. So the volume is going down and the energy of each photon is increasing as you go back in time. So this produces a very interesting effect. Have you heard of have you heard of inverse Compton scattering? Right? You know of inverse Compton scattering. So that's what you see in very high redshift clusters, because the CMB, there are X-ray photons within the cluster. And then there are the CMB photons. Okay? And the CMB can be inverse Compton scattered by the high energy particles in the cluster. So you can see the CMB enhance in the direction of certain clusters. That's called as the Sunyaev-Zeldovich effect. So that is primarily caused by the strong dependence of the CMB energy density on redshift. Hubble parameter. this is just the definition of the Hubble parameter, which is the A dot at any t divided by A of t. That is h, and h naught is basically A dot at the present time divided by A of at the present time, which is 1, of course. So it just gives you what is the current rate of expansion of the universe. And so its units is kilometers per second per megaparsec. Can we write an expression for A of t or Z of t independent of cosmological parameters? So here we didn't involve any of these 3 numbers to write down these equations. So the answer to that is no. You cannot write down an expression for A of t or Z of t independent of cosmological parameters, which also means that if you can measure A of t and Z of t, then you can measure the cosmological parameters, the best fit cosmological parameters.
So we want to measure the redshift using that equation.
Yes. First equation?
So we know the observed wavelength.
Yes.
How do we get that line?
That's from the lab. You have to identify the lines. Suppose there are multiple lines. You can see, okay, this is H alpha, this has to be H beta, because there's a certain ratio of the wavelengths, right? So once you identify that in my observed spectrum, this is H alpha line, then you put that observed wavelength of that line in lambda naught. And from the lab, you know. Yeah, but not all of them are seen. See, remember, 70% of the universe is just hydrogen. So you will not see gold lines and silver lines in the spectrum. Okay, you will only see hydrogen lines mostly. And the ratio also of the wavelengths remain constant. So if you see the several lines of hydrogen, H alpha, H beta, H gamma, H delta, you know what is the ratio of their wavelengths, because you know the lambda E for all of them. So you don't have to fit only one line to get the redshift. You should ideally fit 5 lines, 10 lines, 20 lines.
Which one would be separate?
No, they will all should give you the same redshift. Within the error bars of measurement, they should all give you the same redshift. Otherwise, there's a problem. So if you identify H alpha and you expect H beta to be at a certain wavelength, then it's not there. It's at some other wavelength. Then this is not H alpha, H beta. This is some other line. There. So it's. I mean, I'm a little bit oversimplifying here, but it's easily possible. It's not a difficult exercise.
We measure the periods of Cepheid.
Yes.
Are they far enough?
No, they are no 1 plus z. You can put the 1 plus z correction, but it'll be very small. Yeah. I mean, we can't see Cepheids at redshift 1, for example. Too faint. Scale factor variation with time. So these are various values of omega matter. But what really matters, so in the early theories, there was also a theory that the universe will collapse in on itself. Okay, so there will be a big bang and then there'll be a big crunch. So these models are now ruled out by the observations. What is only present now is basically this model. Omega m 0.3, omega lambda 0.7. Universe is not only expanding forever, the expansion is accelerating. So the slope of this curve is continuously increasing. And here is where we are now. So the critical density, which determines, the critical density is the density which determines whether you will fall back or you will accelerate forever or expand forever. So that critical density is given by this expression. So if you can measure H naught accurately, you can determine whether the universe is going to expand forever or it's going to contract. eventually. So it turns out it's going to expand.
M means there and there's pulling inside, pulling in the universe.
Yes,
Dark matter with dark energy
pushing it outwards. Yes. So it has a, I mean, yeah, you add them together, but this is a sort of repulsive thing. This is an attractive component.
So if it's equal, then it's static.
Huh?
0.5.
If it is 0.5, no. It's not static. It's not static. It will still be flat. I don't know. I have to think about this, but I don't think it will be static. Luminosity distance is, so there are multiple distances in cosmology. Okay. Fortunately, they can be defined in fairly unambiguous ways. Why is there multiple definitions of distance? Because I calculated distance to some galaxy now. Suppose it's 10 billion light years away, right? Yeah, that means the light has traveled for 10 billion years to reach me. Now that galaxy is no longer in that place because it has moved on, traveled for more 10 billion years. So how do you actually define a distance? Where is it now? Was it when the light was emitted? Okay. When the light was emitted, of course, the distance could have been much less from us, right? Because it has continues to move out. So you define a luminosity distance, which is basically you measure the flux and you know the flux luminosity relationship. Use that to define a distance. Simple. Or you do angular diameter distance. You know that the angular diameter of, or the solid angle in this case, right, is a certain, is dependent on the radius and the size. So for one dimensional, you know this formula, the length of an arc S is equal to r theta, right? So you define theta in such a way that it's S over R. Or in this case, in the case of a solid angle, it is pi r square over omega, okay, where omega is the solid angle that that particular galaxy projects onto you, and that will give you an angular diameter distance. And it turns out it can be shown that the luminosity distance and the angular diameter distance are related by this expression. So there's a 1 plus z square factor. And the look back distance is basically how long has the light been traveling towards you. So if it's been traveling for 10 billion years, right, you are looking at the universe as it was 10 billion years in the past. So these quantities depend on the cosmology. So this is the luminosity distance. This is the look back distance. And this is the angular diameter distance, all as a function of redshift. Now look at this curious thing about the angular diameter distance. It's actually decreasing as you go to high redshift, which means beyond a certain redshift, initially when you are here in this regime, as the object goes further and further away, it will become smaller and smaller. But once it goes, I think that redshift is about 1.6 or so. Beyond that redshift, the object becomes larger and larger, not by very much, but slightly. So a galaxy at redshift 1 will look slightly smaller than the same galaxy if sitting at redshift 3. So counterintuitive, but true. And that is related to all this dark energy and the expansion of the universe and so on. So this is a plot of the look back time in gigayears as a function of redshift. So if you see a galaxy at redshift 6, you say that it is approximately 12 billion years in the past. That's how you interpret this. This increases monotonically, but relatively slowly at high redshifts. So this is a plot of the size So as I said, the scale factor today is 1. And the density today, which is also 1, right? And this is the mass energy density evolution with scale factor. So in the early part of the universe, for the first 60,000 years or so, we lived in what is called as the radiation era, where the radiation energy density was higher than the matter energy density. At that point, there was a transition. We entered into the matter era, and up to 9.4 gigayears after the Big Bang, we were in the matter era, where the baryonic matter as well as dark matter together, they dominated the radiations. Then, some few gigayears ago, we are at 13.7 right now, remember. So a few gigayears ago, we crossed a point where the dark energy began to dominate. But notice the curious thing about dark energy. Why does it dominate? It dominates because its equation of state seems to be that it is not, it's constant per unit volume. So you take empty space and you double it in size, make it 8 times in volume, your matter density will fall to 1/8, correct? But the dark energy and density will remain the same, and the total dark energy in that volume will remain will be the 8 times larger. Density remains the same. That is why as the universe expands, dark energy becomes more and more powerful. So as the universe expands, not only will the acceleration increase, but the rate of increase of the acceleration will also increase. So the universe is just flying apart. Nothing can stop. Yes. So some people say it's like vacuum energy. Yeah, but of course, it's not that quantum mechanical vacuum energy, right? It's not like that because it's off by 120 orders of magnitude. But there is something where as space gets created, dark energy gets created for free. And it's a repulsive kind of. Huh? It is opposing the contraction. It is opposing gravity. So it's like an anti-gravity kind of force. So it's got energy, but its energy is like a repulsive energy, not attractive energy like that. Sorry? Yeah, it's created. It's already created. We are already in the middle of it. It happened about 3-4 gigayears ago. Okay, there's no getting out of it. It's growing more and more powerful now. And that is why it has this curious shape. The density is constant. It's flat. Right? Now people are, of course, was it always like this? Is there some slope to this? All that is people are trying to do. So this has, of course, led to the theory of the accelerating universe. And this plot encapsulates how we discovered that the universe is accelerating. So we've measured the distance to different type 1a supernovae at different redshifts. And they figured out, so this was the old model. And this was the best fit model. So all the supernovae seem to be on this side of the curve rather than if I think this, I don't know what this middle model is. Yeah, that is the middle model. And this is the current model. And the dashed line is omega matter is 1, omega lambda is 0. Of course, this is from the 1998 paper. This experiment has been repeated many times. Many people have found the same result. So now you can believe safely that the universe is accelerating. Now, instead of dark energy, there are, of course, many other theories which say, no, dark energy doesn't exist. It's caused by something else. All that is there. But we don't know what. Okay, so the last topic, which I'm going to take an extra 10 minutes to speak about, is active galactic nuclei. We have already encountered many of the concepts in this, so this will go fast. So emission from the hot accretion disk around the supermassive black hole, and sometimes from relativistic, sometimes beamed jets and lobes. So we look at them. And about 10% of massive galaxies are AGN, or perhaps it is more correct to say that all galaxies are AGN for 10% of the time. So there is a duty cycle of these AGN. They turn on and they turn off. And this is probably the correct statement. Optical AGN spectra have strong blue continuum and many emission lines. And there are many, many different kinds of active galaxies, Seyfert-1, Seyfert-2, QSO or quasi-stellar object, quasars, blazars, BL-lacs, radio galaxies, type 2 QSOs, etc. So it's a big zoo. And you have a whole course again on AGN where you will learn about the phenomenology of these objects. This single plot encapsulates to me why AGN are so different from other galaxies. So what is shown here is a CD galaxy, a bright, massive, elliptical galaxy at the center of a cluster. And that is its spectral energy distribution. So it sort of peaks in the optical, infrared, and then it falls off. This is a quasar. So it is much, much brighter than even a CD galaxy, right? And it's this is a very bright quasar, and this is a very bright galaxy. So they're not typical objects, but the brightest galaxy and brightest quasar have been shown. And going all the way from radio to gamma rays, it is just shining brightly. Just shining brightly. And this is a 3C73, 273 quasar, which is the nearest quasar. It happens to be a fairly bright one. So sometimes these radio jets come out in both directions from that hot accretion disk. They come out perpendicular to the accretion disk, and then they collide with the intergalactic medium. And then that jet. So what is the jet? Jet is basically particles, relativistic charged particles moving at very high speeds. Obviously, they'll produce synchrotron radiation. So this is the pink thing is the radio map, and the background is the optical image of the galaxy. It comes right out of the galaxy, and sometimes the galaxy is typically 20-30 megaparsec, kiloparsec in diameter. This can be megaparsec from end to end. It's enormous. This is a cluster-sized spread of these things, and so these kind of galaxies can be effectively studied at low frequencies, and there are many studies with the GMRT, for example, of these kind of objects. So this is an example of the inverse Compton scattered CMB. Okay, so what that happens is the CMB photons actually get scattered into the X-ray band from the lobes of these galaxies because they contain high energy particles. So the particles lose energy, the CMB photons gain energy, and the whole thing just brightens up. So the radio lobes are very brightly seen in the X-ray band, which you wouldn't see otherwise. This particular galaxy, which we discovered some years ago, is at a redshift of 1.3. So it's 9 billion light years away, and it's growing brightly in the X-ray only because of the inverse Compton scattering of the CMB photons. Seyfert-1 galaxies, these are typically the AGN will be at the center, and the host galaxy will typically be a spiral galaxy like the ones you see here. This is the spectrum. So what we had done was we took many thousand Seyfert-1 galaxies, and we just combined co-added their spectra together after aligning them properly. and you get this kind of composite spectrum. So what is it dominated by? Emission lines. And there is a very, very steep blue continuum. So in the short wavelengths, as you go to shorter and shorter wavelengths, the flux keeps on increasing. This is the way in which Seyfert galaxies or quasars can be easily discovered. You just measure the in some UV filter and in some optical filter, you'll find that it's quite bright in the UV filter. So we say they're very blue cores. And this is a composite quasar spectrum, which was done many years earlier. Again, they're similar. They are like the Seyfert galaxies. You see a very strong blue continuum. Okay. And you see so this is the Lyman alpha break. This is the Lyman alpha emission line. You see a lot of metal emission lines over here. So unlike in galaxies, Lyman alpha forest, where you see absorption lines corresponding to these metals, in quasars, you actually see them in emission. So there is a unification model which states that the quasar structure is basically like this. So you have a black hole at the center. Around that, you have a hot accretion disk where the material is falling into the black hole. The inner part of the accretion disks is very hot. They are emitting X-rays. And as you go further and further out from the accretion, along the accretion disk, you will get fainter and lower and lower temperatures, and therefore emission at longer and longer wavelengths. So all your all the way from X-ray emission to infrared emission, all of it is coming from this region. There are also clouds of gas that surround this. So very close to the black hole, you have what are called broadline clouds. These are moving at very high speeds, and therefore their Doppler broadening is high. So they produce broad emission lines. Further away, you have narrower lines. Clouds that are moving at lower velocities, Doppler broadening is less, and therefore you get what are called the narrow lines. So if you look at a quasar from this direction, then you will see both broad lines and narrow lines. These are the type 1, like the Seyfert 1 galaxies or type 1 quasars. However, there is a dusty torus, a donut-shaped object that surrounds the accretion disk. It's very dusty. So if you look around along, let us say this axis, you may not even see the quasar. However, you'll be able to, if there is a radio lobe, so this is where the radio emission, it's only shown in one direction because it doesn't exist in every AGN, the radio lobe. It may not be active. So the AGN itself may be active, but there is no radio emission. So if you look at it from this side, then you'll see a radio lobe here and you'll see a radio load here. And so all of these things basically tell you what you will see it as: narrow line radio galaxy, broad line radio galaxy, radio loud QSO, optically violent variable PL lac, and Seyfert 2, Seyfert 1, radio quiet QSOs, etc. So this unification model brings together the whole zoo of active galaxies and says that they're basically the same kind of objects. There are only two variations. One is the viewing angle can be different, whether you're seeing the accretion disk directly or it's obscured by the dusty torus. That is one. And whether the radio emission exists or not. The radio mode is on or it's off. And this seems to have been quite successful in explaining the universe. Now, these quasars were very, very active at between redshifts 2 and 3. And this was also the age when the star formation rate density seems to have peaked. So lots of things were happening at that time. The quasars were all active. Maximum numbers of galaxy mergers were happening, and maximum amount of star formation was happening in galaxies. So that is certainly true. Now JWST, so this is from my paper in 2006, but now measurements of these numbers have been extended to high redshift with JWST. And those numbers are not here, but they're coming out to be here. So it may be that this star formation rate density is relatively flat afterwards. So this plot will probably need to be modified. So what have we plotted on the y-axis? The star formation rate, but in terms, not in terms of per galaxy, but in terms of co-moving volume. So how many stars are you forming per megaparsec cube co-moving? Okay, so we come to the end. I think I've covered everything that is there in your syllabus. And we've also had one extra lecture on exoplanets, which is not part of the syllabus. I think it should be, but now we covered that. I also wanted to cover a little bit on gravitational waves, but I've not covered that. But I think you will encounter that anyway, because there is gravitational waves, at least in Ayuka, it's everywhere in the atmosphere. So you pick up the basics of gravitational waves anyway. But I hope I have equipped you enough. The goal here is to understand the jargon, the broad idea. What are the physical parameters astronomers measure? How do they go about measuring those parameters? And the goal is to get you to a level where you can start thinking of reading some scientific papers, and you can start attending the colloquia and seminars that we have here. And try and grasp. So that I would strongly encourage you. Please, I mean, there are very few places in India, or I think there are no places in India which have the high number of seminars and colloquia that NCRA and Ayuka between them have. So please attend the talks. Don't, even if you know what area you're going to work for your thesis, please do at least at this stage attend all kinds of variety of talks. Because you may suddenly find that, no, I find that more interesting. You'll be able to learn a lot by attending as many talks as possible. So that's my only thing, and you'll be asked for your feedback. So I'd love to get, I'm only teaching this course for the second time, and last time I taught it 5 years back, pre-pandemic. So I would love to get feedback. So in your feedback forms, you have to tick some numbers, but you also have a text box where you can give specific comments. So please feel free to give comments on the teaching, the material covered, teaching style, the exam, whatever it is. Yeah, so we come to an end and we are done.